So let us start with the divergence theorem now. So here, if you see this equation represents divergence theorem. So left side equation is the volume integral of divergence of any vector is equal to closed surface integral of the same vector dot ds bar. Okay. So now here, let me explain what is the meaning of this equation and what is the statement of this divergence theorem. Okay. So for that, first consider the region we have considered in this theorem is nothing but volume. Okay. So volume is the region we have considered here. I light. The region we have considered is a volume. Okay. Now I require what is the boundary for this volume. Okay. So actually you consider any finite volume. Okay. If you want, you can add any finite volume. For any finite volume, what is the boundary? Okay. For example, you consider, so there is a cubical volume. Consider this cube. Yeah. So for this cubical volume, what are the boundaries? You can observe that it is a finite volume. For this finite volume, if I ask you what are the boundaries, you say that the top surface is the one boundary, next is a bottom surface, then right side surface, left side surface, the front surface and back surface. Okay. So totally this cubical volume is enclosed by these 6 faces. Okay. So completely these 6 faces are the boundaries. Now you just observe all these 6 boundaries or 6 faces. So these boundaries these boundaries will form a closed surface or open surface. Definitely it is a closed surface. Okay. So boundary for this volume is a closed surface. Closed surface. So I say that for any finite volume, boundary is a closed surface. Okay. So not only this shape, you consider any finite volume like a spherical volume. So it is a spherical volume. Spherical volume. Okay. For this spherical volume, what is the boundary? Entire surface of the sphere is the boundary. Okay. So entire surface of this sphere will form a closed surface or open surface. Definitely it is a closed surface. Okay. So like you can consider any kind of volume, like one more example I consider. This is cylindrical volume. Cylindrical volume. Okay. So here for cylindrical volume, what are the boundaries? You say that one is the top surface is one boundary, bottom surface is another boundary, and then lateral surface or side surface is the another boundary. Okay. So combinedly all these 3 boundaries represents a closed surface or open surface. Definitely again it is a closed surface. Okay. So finally I conclude here, for any finite volume, boundary is a closed surface. Boundary is a closed surface. That's what I'm going to write here. So region we have considered is a volume and boundary for this volume is a closed surface. It is a closed surface. Okay. Now, so just you understand this concept. So for any finite volume, boundary is a closed surface. Now let me explain this divergence theorem with the help of an example here. Okay. So let me choose a cylindrical volume. Yeah. So sorry, not cylindrical, cubical volume. Okay. So let us consider this closed surface or it is a volume. Okay. So inside this box, I consider there is a charge of 5 coulombs. Okay. Plus 5 coulombs. Now, you know that the charge will exhibit electric field or the surrounding the charge, the field present is a electrostatic field. Okay. So these, what is the direction of electric field or electric flux due to this positive charge? electric flux always will move away from the positive charge. The flux will move or field will move away from the positive charge like this. It moves in all the directions. So like this. Okay. So simply flux is moving or field is moving away from the positive charge. Away from the positive charge. Okay. So now just see here. Observe this one. So from this diagram, I will write a statement. The statement is that, so flux is leaving the volume. You know that this is a box or a volume. Inside the box there is a charge. So flux is leaving the volume. Okay. So I am going to write here the flux leaving the volume. Flux leaving the volume. Yeah. So here, how do you say that the flux is leaving this volume? So actually, whenever flux will cross its boundary, so then we say that flux is leaving. For example, if I draw flux line like this, a small flux line, okay. So now you say that, is this flux is leaving this volume? No. So this flux is not leaving this volume. The reason is that this flux is not crossing its boundary. Okay. Whenever the flux crosses its boundary, then we can say flux is leaving. So what I mean to say here is, so flux leaving the volume is nothing but flux crossing its boundary. Okay. So flux leaving the volume is nothing but flux crossing its boundary. Flux crossing its boundary. Yeah, fine. Okay. What is meant by its boundary? What is the region we have considered here? Volume is the region we have considered. Then what is the boundary for any finite volume? Already we know that for any finite volume, boundary is a closed surface. Okay. So this boundary is nothing but closed surface. Okay. So now once again we can read here, the flux leaving any volume is equal to the flux crossing its closed surface Okay. So that means here what we are doing here is, with the help of divergence theorem, we will have an alternative methods or two methods to find the same quantity. Okay. So for example, in this diagram, I want to find flux leaving, how much flux is leaving this volume. Okay. For example, I say here, so from the diagram I can count how many flux are leaving this volume. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 flux lines are leaving the volume. Okay. Similarly, you count how many flux lines are crossing its boundary. Okay. So there are boundaries shown here. How many flux lines are crossing its boundary? So here you can observe in the diagram, again it is 13. Again it's nothing but 13. Okay. That means we are finding the same quantity either directly counting flux leaving the volume, or we are finding the same quantity by observing or by counting flux crossing its boundary. Okay. So simply this is called as a divergence theorem. The meaning of divergence theorem. Divergence theorem gives us alternative methods to find the same quantity. There is a flux leaving the volume. Okay. Here, to find the flux leaving the volume, we use a left side equation. Okay. What does divergence represents? Divergence finds amount of diverging field or amount of leaving field. Okay. So this divergence finds amount of flux leaving, Okay. Flux leaving which region we require? Volume. That's why you apply volume integral. Okay. So this entire left side equation will give us the flux leaving the volume. Okay. That is equal to right side quantity. Okay. Here right side we have a closed surface and dot product with the same vector field. Okay. So this dot product will give us, so flux crossing this closed surface. Okay. So flux crossing its closed surface. Okay. So this entire statement is written in the form of mathematical equation. Okay. This mathematical equation is nothing but divergence theorem. Okay. So and its meaning is given by this statement. So this statement gives us the meaning of divergence theorem. Okay. So let us write down this divergence theorem in the form of formula. Okay. So in examinations or in electromagnetic fields, we use this theorem as a formula. Okay. So let me write down here. This is volume integral of divergence of A bar into dV is equal to closed surface integral of same vector A bar dot ds bar. Okay. So this is the formula of divergence theorem we use in the electromagnetic fields. Okay. Or if you want to verify this theorem, we can verify with the help of units. What are the units left side of the equation and what are the units right side of the equation? Okay. So just see here. So here we don't know what is A here. I consider units of A same. Okay. So something we don't know, units of A bar. What are the units of del? 1 by meter. What are the units of dV? dV is called as a volume element or a differential volume element. Okay. So volume may be smaller or bigger of any size. So volume units remains same. Units of volume is meter cube. Okay. So left side we have this equation and right side vector A bar. We don't know units of A bar, leave it as it is. And what is ds bar? ds bar is a differential surface element. Okay. So surface will have units of meter square. Will have units of meter square. Okay. So just observe that units on both sides are same or not. So here 1 by meter cancels with the meter cube, you get meter square. Okay. Units of A bar into meter square, units of A bar into meter square. Okay. So in this way also we can verify this formula. Okay. So this is the divergence theorem. Okay. Next we will move on to another theorem called as a Stokes theorem.